So guys, welcome you all to this video. Here we will cover the topics which were left in our discussion of sequence of real numbers. So we will start this video with the concept of Cauchy sequence. Then we will discuss lim sup and lim inf regarding sequence of real number. Okay, so let's get started with Cauchy sequence. The basic definition of Cauchy sequence is something like that. Okay, suppose you have sequence xn, sequence of real number, and this sequence is said to be a Cauchy sequence if after a certain number of terms, okay, difference between two terms of that sequence, that is xm minus xn, can be made less than epsilon for all mn greater than n. Okay, that is the basic story. After certain term, that is after nth term, the difference between any two consecutive terms can be made as small as we please. That stands for epsilon. Okay, so the definition is something like that. For epsilon greater than 0, however small there exist n belongs to z plus or natural number such that xm minus xn less than epsilon for all mn greater than n. Okay, or there is another equivalent statement, that is xn plus p minus xn less than epsilon for all n greater than n, and p equals to 1 2 3 and so on. Okay, that is the main story for Cauchy sequence. Fine. All right, now here I will give you some example for you, and the basic example, it is example number 1, that is xn equals to 1 by n. Take this sequence. In fact, this sequence is a Cauchy sequence, that is xn minus xn. Try to find out this difference and take say 1 by n common, so it will be m minus n, and that part can be made less than 1 by n, and if we take 1 by n less than epsilon, then what we are getting, look at 1 by n less than epsilon. Fine, so this will imply n greater than 1 minus epsilon. So if we take n equals to box function of 1 by epsilon plus 1, that belongs to the set of natural number. So what we are getting is for epsilon greater than 0, for epsilon greater than 0, however small, we are getting, that is there exists n, epsilon belongs to n such that here xm minus xn it is less than epsilon for all mn greater than n epsilon, where in this particular example this n epsilon, it is nothing but box function of 1 by epsilon plus 1. Fine. Thus after this nth term, the difference between consecutive two terms, that is xm minus xn, can be made less than epsilon. That is the sequence xn equals to 1 by n is Cauchy sequence. Okay, thus we show that a sequence is Cauchy. There are many more examples for you as well, like verify. Here I am giving you some work to do. Verify which of the following is Cauchy. Okay, so the first option, xn equals to 1 plus 1 by 2 plus 1 by 3 plus 1 by n. Second one, xn equals to 1 minus half plus 1 by 3 minus 1 to the power n minus 1 1 by n. Third one, xn equals to 1 plus 1 by factorial 2 plus 1 by factorial 3 plus 1 by factorial n. Okay, so verify which of the following sequence is Cauchy sequence. Okay, fine. So that will be your work, and let me know in the comment section that which one or R is going to be your answer. Fine. Here I am just giving you the basic notions so that you can go to any textbook whatever I have already referred to you and study more examples and concepts as well. Okay, some results are there, but here I am giving you one keynote regarding this topic, that is every Cauchy sequence is convergent where in real number system, that is in R Cauchy implies convergent and convergent sequence implies Cauchy sequence in R. Okay, but it is not true in general. Whenever we have a matrix space which is complete, in that case Cauchy implies convergent. But if we take a matrix space which is not complete, in that case Cauchy sequence may not be convergent. Okay, for that you have a very simple example, xn equals to 1 by n defined on, in fact defined on 0 1. Okay, if we take this sequence on this interval with usual metric, then this sequence is not convergent in that matrix space. Okay, that is 0 1 with a usual metric. Okay, so in that case it is not Cauchy sequence in that space. Okay, fine, because here in R with usual metric it is a complete metric space, that's why Cauchy implies convergent and vice versa. Okay, fine. That was for Cauchy sequence, more or less you can say a brief idea about it, and now we are coming on to lim sup and lim inf concept. Lim sup and lim inf. In fact, for a bounded sequence, whenever we say a bounded sequence, that means bounded above, and the another case is bounded below. Whenever we have a bounded above sequence, then we have upper bounds, and for the case of bounded below we have lower bounds, and for bounded above case we have upper bounds. The number which are greater than any upper bound, these are also upper bounds, and the numbers which are lesser than a lower bound, these are also lower bounds of that particular sequence. So the thing is, whenever we have least upper bound, that is LUB, we call it as lim sup, or in another notation lim here. Okay, and the greatest lower bound, that is GLB, we call it as lim inf. In notation this one. Fine. So this is the idea for lim sup and lim inf, and if we want to express all these things in mathematically, then what we have, just take the flavor. What actually it says that suppose we have mu and we call it as lim sup of that particular sequence xn. Fine. So that means we have mu plus epsilon, mu minus epsilon. It is any neighborhood what we are taking here. Epsilon, it is greater than 0, a very small positive quantity. Whatever we wish, we can take it. Okay, so we have a neighborhood like this way where epsilon greater than 0, and this mu, it is an upper bound. In fact, in our previous discussion, from that discussion we are getting that mu is the least upper bound. Fine. That means mu to mu plus epsilon. Here in this region only finitely many xn's are there, correct? And in this region infinitely many members of xn are there, correct? Fine. So it says that for every epsilon greater than 0 there exists n belongs to the set of natural number such that n greater than this capital N implies xn less or equal to mu plus epsilon. That is for finitely many members of that sequence, and xn greater than mu minus epsilon, that is in that range. Okay, this one holds for infinitely many n. Fine. This is the main story of lim sup regarding some mathematical point of view, correct? Similarly we have, suppose lambda is equal to lim inf of xn sequence. Fine. In that case we have lambda and lambda plus epsilon, and here lambda minus epsilon. Fine. So by default it is lower bound, and it is in fact greatest lower bound of that sequence xn. So here this part, it is for infinitely many members of xn. Okay, and this part may contain finitely many members of xn. Fine. All right, this is the idea for lim sup and lim inf. Now here I am giving you some properties regarding lim sup and lim inf. So the first property, it is lim sup of xn plus yn less or equal to individually xn plus lim sup of yn. Second one, lim inf of xn plus yn, it is greater than lim inf of xn and lim inf of yn. So this one first, this one second property, correct? Okay. Third property, you have if xn less or equals to yn for all n greater than n, then lim inf of xn less or equal to lim inf of yn and lim inf of xn less or equal to lim sup of yn. Fourth property, it says that the product, regarding the product xn yn less or equal to individually their product of lim sup. Okay, and the fifth property, here another thing is there, lim regarding lim inf, that is xn yn greater or equal to lim inf of xn into lim inf of yn. And the last one, xn inf less or equal to lim inf of xn minus yn, this one less or equal to lim sup of xn minus yn, and this one less or equal to lim of xn minus lim sup of yn. Okay, so these are some properties regarding lim sup and lim inf, and if you are interested, then you may have some look on the proof in any textbook whatever I have already suggested to you. You can go there and check it out. As these are all one-sided results, so obviously converses are not true. For that obviously you have some counter examples as well. I hope that you will study those counter examples, and we will meet soon in the next video, in which video we will tackle some questions regarding all these properties, and the things will get more clear to you. Okay, so meet you soon in the next video, and bye.